Leslie, take it away.
The artist formerly known as Prince once said, "Each day is new beginning." I'm Leslie Oliver Karpas, president and co-founder of LexSet, where we're bringing a new beginning to how computers see the world. AI is only as good as the training data that you show it. And as the mixed reality industry transitions away from target-based AR to truly spatially aware content, the way that we train computer vision systems will be increasingly important. Today, I'll explain some of the fundamentals of training CV systems, unpack how synthetic data is improving how we train them significantly, and then take a look forward at how 5G is about to change and catalyze computer vision in ways that will be hugely enabling for the industry as a whole. So first, let me establish some of my credibility. I was last year's winner of the startup competition here at AWE, getting this Auggie trophy for Startup to Watch, which was an amazing moment for me. Additionally, last year, we won a bunch of other awards, including being honored to be selected as one of Verizon's Built on 5G Challenge winners. And so this has given us a really close look at 5G technology, being able to work with that. Then also, I worked with Ori being selected as one of his inaugural RLab participants, the mixed reality accelerator that he started in New York last year. So what is computer vision and what can it do? Let's take a deeper look. So first off, in its simplest form, computer vision can do things with individual objects or individual photos. The basic form of computer vision is called image classification, which is applying a single label to an image. What is this image? Then you have deep classification or nuanced classification, which says, what is in this image at a really detailed level? So the second image, instead of just a cat, is an orange and white Maine Coon kitten. So you see how we got to a deeper level of nuance there and classifying what that is. Then you have something that's a little bit more detailed called classification with localization, which is what is this thing and where is it located in the image? So then if we get a bit more complex, we can get to what task computer vision can do with multi-object recognition. So object detection is the core of those. It's basically multiple forms of localization. So that's a dog, that's a cat, that's a duck. They're at these parts and locations of the image, as well as, that's 90% chance that that's a cat, that's 65% chance that that's a duck. The computer vision is letting us know the confidence that it has for a given item. Then you have what's called semantic segmentation, which is tracing all of those objects. So understanding the boundaries of where one object starts and stops. And then lastly, we have what's called instant segmentation, which is counting all of the individual times that we see a cat or a dog, and then tracking that that's cat one, that's cat two. And this basically is the set of things that computer vision can do. Now, these tasks, these abilities have a tremendous vast array of commercial use cases that I'll unpack quickly right now. Most of you have heard of Amazon Go, which is their cashierless checkout store. That takes computer vision and uses a couple of its functionalities. One, being able to track people as they move around the store, and two, being able to track the products that people are putting into their basket and walking out of the store with. So let's look at some of the other applications that make computer vision a $25 billion plus industry. It's growing really quickly right now. So two categories that we'll kind of break these down into, one being robotic computer vision abilities, and then the other being mixed reality computer vision use cases. So first and foremost, you've got what's known as planogram compliance or inventory robots. Robots that can drive down an aisle, identify what products are on the shelf, what products are in the right or wrong place, and what products need to be restocked. Then you've got robot vacuum cleaners, which I'm sure you all are familiar with, and using CVAI to help those things navigate around the space, avoid obstacles, avoid humans, and make sure that they're doing a really efficient job of cleaning. Then you've got a whole sector of fulfillment robots, robots that can drive around the warehouse, put products on a shelf into a bin or a basket so they can be shipped out. And then cashierless checkout, which I mentioned just a moment ago when I talked about Amazon Go. That's about to get a lot more prevalent. On the other side of things, we've got mixed reality uses for computer vision, particularly relevant for us here at AWE. So the planogram compliance that was being done before by a robot could easily be done by a human with a phone, tablet, or heads-up display. They could walk the aisles and make sure that everything is where it should be. In the very near future, we'll see spatially aware content in gaming and industrial applications, such that you could have a holographic character sitting in a real chair across from you, or pick up a holographic object off of the real table in front of you. Then there's a whole host of industrial applications around part recognition and wayfinding. So that's things like, what is this part and where do I put it away? Or this part is broken and I need a new one, or this is broken and I need to know how to fix it. These are all great applications of industrial XR. Then last but not least, something that's so common that we kind of forget that it's a part of this set of uses is visual search. Things like Google Lens or Pinterest Lens that allow us to look at a product and find other products that look like it, or look at an image and directly shop the products that are in that image. So now let's talk about how we train computer vision AI. What is this process like fundamentally? So at its core, it comes down to a task known as convolution. Convolution is looking at an image and thinking about every pixel as a number, then creating a summary of those numbers that's a simplified version of the image, essentially a way to find patterns within the image at a broad strokes level. The most common form of computer vision AI is called a convolutional neural network, or a CNN. And what it's doing is it's sweeping the image, looking for different patterns and clusters, and saying that pattern is X percentage dog, this percentage cat. And at the end of the output, you get a series of scores of the things that AI has been trained to recognize from a pattern standpoint. So to train those systems, one of the dirty secrets of AI is that it requires a huge amount of human labor. And let's talk about that and why it is less than optimal. It starts with having to capture large libraries of photos or scrape photos across the internet. Then once you have a big data set of images, you have to send that to be labeled, to be annotated. And so there are annotation workforces across the world that have people clicking monotonously labeling objects so that they can be fed to AIs. Then we train the system, and that can take weeks or longer, depending on how deep and complex the neural network is. It's also very expensive in terms of compute. And at the end of this, you evaluate, and you're inevitably going to find problems and issues with the AI, so you're going to start the process over. And before you know it, months have gone by and a lot of money has been spent. It's suboptimal, but that's the status quo today. And so let's talk about some of the issues with that approach. So first off, as I said, slow and expensive, not great. Then those human annotators, they're not perfect. Any errors that they make labeling the data will trickle into the AI. And so that's sort of a garbage in, garbage out problem. Then there's a lack of edge cases in the data. So anomalies are situations that are relatively uncommon that don't make it into the data, and this creates different forms of bias. You've got explicit bias, which is like not having subject matter. For example, if you're training an autonomous vehicle, not having enough yellow lights because red lights and green lights are way more common. Or you have implicit biases, like the fact that humans took a lot of the photos. The camera angles tend to be the same, or they tended to take the photos during the day, so the lighting tends to be the same. And so lighting bias and camera bias are two of the most common forms of data bias that people tend to not be aware of when they start their training. So synthetic data is a way to get around all of these issues. And so let's unpack what synthetic data is. So first, there are synthetic data generators from video game engines like Unreal or Unity or Grand Theft Auto. And that's a whole world to use traditional techniques of gaming to create content. Then there's what are known as generative adversarial networks, or GANs. This is an image from StyleGAN, which is something that a lot of people have played around with and talked about because it can generate artificial human faces from existing photos of humans, which is a little bit creepy and got a lot of media attention. And last but not least, you have LexSet's approach, which is procedural environment generation, where we have algorithms that can place objects and scenes randomly, but with rules. So I'm going to take a look at that at a far deeper level. The big benefit of synthetic data is that we get to compress that data capture step. and that data annotation step into a far faster and efficient data generation step. And so these are all images that our engine has produced, taking lots of different 3D objects and putting them into scenes that are procedurally created. Then when we train the AI and see how it performs, we can rapidly tweak how the data is being produced in the generator and then plug it back into the AI immediately, getting to a very efficient, unbiased AI in a matter of days instead of months. So synthetic data isn't new, but up until recently, it's had a lot of issues that have held it back. So the first issue and the biggest one is something known as overfitting. You teach AI how to recognize a rendering and not real life. This is something that LexSet is proud to have solved. And the way that we did that is by taking photorealism very, very seriously within the images that our engine generates. The second problem is that traditionally it's labor intensive to make 3D scenes. Running an animation studio, kind of like Pixar, or a video game studio like Activision, that resembles the video game technique base. And what LexSet has done is figure out a way to do this algorithmically so that we're not so labor intensive with the scene creation. One drawback is it is reliant on having a large library of 3D content. We have a content library of over 100,000 models, but not everybody is fortunate enough to have that access to that many photorealistic models. And we'll be working later this year to make that a little bit more available along with our tools for synthetic data generation. And then last but not least, there are a lot of variables that have to be dialed in to really precisely control the randomization scope, the domain randomization, as it were. So what does that look like? For LexSet, that's the ability to have these algorithms place objects in the spaces, and then we can generate the annotations as easy as changing the rendering pipeline. And this is very, very powerful for accurate AI. Not only does it mean that we can do complex annotations, things that would take a human a really long time to do if they were manually tracing the objects in the scene, but we can also do things that humans can't do, like simulating LiDAR or depth or sonar. And then, as I said before, our pipeline is very, very interested in having the most accurate lighting possible. And that is how we have solved the overfitting problem, by getting really into reflection, refractivity, and using PBR materials or photorealistic materials. In order for this to create really good AI, we have built a tool to segment 3D objects. So we have a tool for humans to label materials and replace materials in 3D CAD, so that we can take assets from being video game or movie grade to LexSet AI grade. So very, very photorealistic. And if you are a content studio or library and you have a lot of content that you would like to make more rich, that is something that we would be happy to do for you. But what this does is it allows us to say that that's wood, that's metal, that's plastic, and getting really, really detailed, not only about how materials look, but having the AI understand what the materials are. And so the effect of this is once we create a scene, we can instantly, as easy as throwing on a rendering pipeline, identify what the objects are in the scene, trace all of the objects in the scene, or figure out the depth or synthetic LiDAR of all of those objects, as easy as changing the rendering pipeline in the runtime. So this is a demo that will be live at Verizon's 5G labs later this year, where we have a small scale model of a 3D printed engine block. We trained an AI on a tablet to recognize all the parts in the engine. And this will be fun for you to go play with. But what's interesting is how we made the data. We took all of the individual parts of the engine and rendered them in thousands and thousands of different environments, lighting conditions, camera angles, occlusion states, essentially pre-simulating all of the ways that the parts on that engine can look, so that our AI is ready for whatever reality happens to throw at it. This is something that we can do with our procedural engine, because once the engine knows what the variables are, it can churn out different versions of that scene over and over and over again until we tell it to stop, which is a great way to have near infinite amounts of data. So now that we understand computer vision, let's take a look at the future about how 5G is about to change it in ways that will be extremely powerful for the industry. As we do that, I need to explain to you a core concept in 5G, which is known as fog-based computing, or compute that happens in between the edge and the cloud. It starts with 5G broadcast antennas, and I promise they don't cause COVID. And then when you combine those antennas with micro data centers, so small racks of CPUs and GPUs. You get something that is known in the industry as a MEC node, or a multi-edge compute node, which means that you now have compute directly at the antenna, very near to the end user. And the effect of this is extremely low latency, extremely high data transfer speeds. So a way to think about this, a way to understand MEC-based computing or fog-based computing, or another name for it is thin client computing. And I see this as a return to something that existed back in the late 60s and 70s, which was when we had big mainframes that were in the basements of buildings and terminals that we all dialed into those mainframes with. That's kind of where we're pointed now. But today, instead of using mainframes in basements, we'll have 5G MEC node antennas. And instead of terminals, we'll have our phones and our tablets. And they're acting as thin clients, which means that all of the compute and heavy lifting is happening at the node. And your device is essentially just a way to portal into that. And this not only saves battery life, but it enables a whole host of really powerful things to become possible. For computer vision specifically, this means that we can get into deeper, more nuanced, more complex neural networks, and that we don't have to compress those networks. So being able to compress a neural network so that it can work on a phone, tablet, or robot has been a really big problem for the AI industry as a whole. And 5G is going to make this go away, which is very exciting for those of us in AI. Being able to put AI networks on these nodes means that we'll also be able to retrain the nodes very, very quickly, which means that if there are changes that need to happen in the field, we can update AIs in a way that we cannot today, which is really great. And then that is because we can generate the synthetic data. In addition to retraining the AI at the node, we can create the data that the AI needs there. And so there's far, far less data to send around the cloud. Another way to think about this is why send a forest when you can? So a trained AI model, or the amount of data that you need to train an AI, is terabytes and terabytes. It can take hours or sometimes even days to move that from one location to another. We see a new way, a better way to do it. And that's taking LexSet's procedural generation techniques, taking an API for that, combining it with a few core 3D assets that are needed for a given use case, sending that to the MEC, and then growing the data and the AI and training it right then and there. And so this is way faster, way more elegant than the traditional ways that we do it. And we're looking forward to the near future where this becomes the best and industry standard way to move complex computer vision systems around the world. And so in conclusion, I'd like you to think about what AI could do if you had infinite data of everything. Thank you so much for your time today. I'm happy to take your questions.
Thank you very much, Leslie. Very interesting talk that you provided. I liked how you coined AI is only as good as its training data. So the question I've got is elaborate a little bit more on the veracity of that data.
Sure, absolutely. So I spoke a little bit about data bias, about how if you don't have a multitude of different camera angles, of lighting conditions, of occlusion states, if you're not simulating the noise and the optics that the end device the AI is going to be deployed on has within it, then you end up overfitting the data. So you teach an AI how to recognize a rendering instead of real life. And so what LexSet is primarily concerned with is how to convince the AI that it's not looking at a rendering when we create that training data. And we have been successful in training very accurate object recognition classifiers with no photos in the data set, just using our synthetic data. And so we see a future where photo collection is completely unnecessary.
Very cool. Thank you. You're talking about lots and lots of high volume data, and I always like to throw out yotta bytes and everything. You talked about 5G though. In terms of practical application today, what about the timing, right? Because 5G is not prevalent yet, and the demands on that infrastructure. Talk about a little bit of where you see then the timing of it and the what I'll call saturation, the reach.
Absolutely. So in the near term, I believe that we're going to see the initial deployments for interesting 5G applications happening in warehouses, and factories, and fulfillment centers, basically functioning as extra long distance Wi-Fi, because it's going to take a while for the major telecos to get 5G antennas deployed everywhere for public consumption. But for industrial and commercial use cases, I think there's a lot of really interesting things that we're going to see happening in the immediate future. And so I think that's where it's going to start.
All right, we're out of time. I want to extend my thank you to you, Leslie, from LexSet, and that concludes our session.
Thanks, Kathy. Appreciate it. Thank you, everyone.